So when you think of what is a chemical reaction, you might be thinking, well, that's something that involves an explosion or things mixing together to bubble and produce something exciting. But from now on, whenever you hear the term chemical reaction, I want you to think of a process that involves reactants transforming into products. So what does that mean? A reactant is something that reacts with something else. So most chemicals, all chemicals. And a product is just something that's formed as a result of that process. So basically, a chemical reaction then, very importantly, always forms something new. So new substance is always formed in the process. So if nothing new is formed, if there's no product, then it's not a chemical reaction. And there are ways that we can recognise that a chemical reaction has actually happened. There are signs of a chemical reaction that we can look out for. So what might they be? You could have a colour change. You could have a solid being formed, and I'll come back to that one. You could have a gas being given off, or the temperature could change. Now there's a couple of them that can be confusing, so we're going to have to go over this. Very importantly, these changes don't include things like melting, or freezing, or evaporating. Anything that's just a change in state doesn't tell you that a chemical reaction has happened, necessarily. So, for example, if I have some water, and that's liquid water, I put it in a cup, and then I put that cup in the freezer. Come back a couple hours later, I take the cup out of the freezer, and it's went from being a liquid to a solid. Now that is a change. Something has happened, right? The state has changed from liquid to solid, but the chemical that I put into the freezer was water. The chemical that I got out of the freezer was water. It's not changed chemically, it's just changed physically. So these four changes here are chemical changes specifically. They're not physical changes. Okay, so if you mix two chemicals together, or two or more chemicals together, and it changes colour, that's a chemical change. If you, for example, mixed two liquids together, and as a result of that mixture, something solid was formed, right? You didn't change the temperature or put it in a freezer or anything like that. It just did it as a result of the reactants reacting together, then that's a sign of a chemical reaction. If a gas is given off during a reaction, that's a sign. And if the temperature changes, but you didn't change the temperature, it wasn't externally done, right? You didn't put it in an oven or a freezer or anything like that. You mixed two chemicals together and the temperature started to change as a result of that mixing, then that temperature change is a sign of a chemical reaction. So basically, did these things happen as a result of you adding things together? Then that tells you it's a sign of a chemical reaction. Okay, so something new being formed, and those are the ways in which we can tell that it's happening. Now on top of that, there are a couple of types of temperature changes that you should be aware of. And these types of reactions that have temperature changes have specific names. So we call these exothermic and endothermic reactions. So what does that mean? Well, an exothermic, which sounds a little bit like explosion, which might be a way you can remember this, is a reaction that will release heat energy, and as a result of releasing that energy to the surroundings, to the environment, it will get hotter. Okay? Now again, very important distinction to point out here. You are not putting it in an oven or externally heating it. Just from the chemicals reacting together, right, just from coming into contact with one another, because of the chemistry that's going on there, the whole mixture is getting hotter by itself almost, right? Which lets you know that it's a chemical reaction and it's not a heat change that you are making to it. It's doing it itself. It's getting hotter. And if it gets hotter, that means energy is being released. And if energy is being released, it's an exothermic reaction. Now the opposite can happen as well. So what if it's an endothermic reaction? Well, in those, It's just the exact reverse. The reaction is absorbing heat from the surroundings, it's taking it in, and as a result of that, the mixture will get colder, or the reaction will get colder. Okay? So the two different types then, exothermic, which gets hotter because it's releasing energy to the environment, which we feel as heat, and endothermic is taking that heat in, away from the environment, it's sucking it in, so the reaction vessel gets colder. And a simple way to remember this, because that can be quite confusing, is that in an endothermic, the energy is entering the reaction, so remember the En, and in an exothermic, the heat energy being released is exiting the reaction. It's just a case of remembering which one gets hotter and which one gets colder. What is an atom? You might be familiar with the idea that an element is a pure substance made of only one type of atom. So pure meaning there's only one ingredient to make that element, and the ingredient is all of the little tiny particles that we call atoms. It's the smallest building block that we know in the universe to make all of the material in the universe, which is true. And that they're really, really small. So for example, this little full stop that I have after the word atoms contains more atoms than there are people alive today. So there's billions and billions of ink atoms, if you like, in that full stop. And that is a good understanding of what an atom is. It's the tiny building block that makes all of the pure substances in the universe. But we can go a little bit further than that, because atoms themselves are actually made up of even smaller particles called subatomic particles. So that just means even smaller than an atom. And those are really what are important when we're thinking about what the atomic structure is like, what actually is an atom. So what do we need to know? There are 3 subatomic particles that we need to know about. And we're going to look at them one by one. So first of all, we have something called a proton. And when you hear the word proton, I want you to think positive. So a positive proton. It's a tiny, tiny, positively charged subatomic particle that makes up part of the atom. Next, we're going to look at neutrons. Again, very, very tiny, makes up part of the atom, but this time there is no charge, there's no electrical charge. Neutron sounds a bit like neutral, which means exactly that, there's no charge, it's neutral. So we have positive protons, neutral neutrons. And I'm looking at these two first because they both live in the same part of the atom. So I will draw some positive protons. Let's just say we have 3, like that. And I will draw some neutral neutrons as well. Now obviously atoms being teeny, teeny, tiny, this is as if I've zoomed right in to an atomic scale to analyse what is inside the atom, but this would be microscopic, sub-microscopic, absolutely tiny. And you'll notice that I've drawn them kind of bunched together. Now this is one part of the atom and it's right in the middle. Now every tiny atom has an even tinier centre, and that is where the protons and the neutrons both live. So we call this part of the atom the nucleus, which is where the protons and the neutrons are. However, there are 3 subatomic particles, so there is something else still to come, and that is the electrons. So what do we need to know about electrons? Electrons are kind of like the opposite of the proton. They are negatively charged. So their job is to kind of balance each other out, and that's exactly what they do in an atom, which I'll talk about in a minute. You'll also notice that in my little diagram at the side, to represent the electron, I've drawn it as a little tiny blue dot. That's because compared to the tiny proton and the tiny neutron, the electron is even tinier. It's super, super tiny. And because of that, and because of its charge, it doesn't live in this nucleus like the protons and the neutrons. The tiny negative electrons orbit round about the outside of the nucleus. And that is maybe where you've seen a shape like that before. So these kind of rings don't really exist, but they just represent that these little electrons are whizzing around the outside of the nucleus. And because they're negative, and the protons are positive in the middle, the little tiny electrons are attracted to this positive nucleus. That's why they don't just fly away and do their own thing. They want to be close to that nucleus because they're attracted to the positive charge of the protons because they're negative. So they kind of just whiz around really, really quickly around the outside of the nucleus. And for future reference, I will call these sort of ring shapes just now orbitals. And an orbital just means a space around the nucleus that the electrons will orbit. So we have positive protons, neutral neutrons, negative electrons. So what does that mean for the charge overall on our atom? Well, an atom is only an atom if it has the same number of positive protons and negative electrons. You'll notice that I've drawn 1, 2, 3 little red dots, 1, 2, 3 little blue dots. And that's not by coincidence, that's deliberate. That makes this an atom because those charges are balanced out. So because atoms have an equal number of positive protons and negative electrons, overall they are neutral particles. So what does that mean? That just means they have no charge. So atoms are neutral overall because they have the same number of positives and negatives, and they cancel each other out. And of course the neutrons don't contribute any charge because they are neutral. Now the last thing that we need to know about this structure is, thinking back to our periodic table, you should remember that going across the way in periods, that's in the rows, that the atomic number is something that starts at 1 on the top left hand side with hydrogen and increases as you go down the periodic table. And I said I would come back to that. So what does that actually mean? Well, an atomic number is something that every element has, and it tells you something about this structure. Because we've said that an element is a pure substance made of only one type of atom. Well, that tells us that every element has a specific type of atom. How do we know what atom is which element? How do I know what element this is? Well, the atomic number tells us that. So each element has its own atomic number, and that number tells me how many protons are in the nucleus of that element's atoms. So, for example, if I look at my periodic table, I will see that hydrogen has an atomic number of 1. So what does that mean? That means hydrogen, if I took an atom, a single atom of hydrogen, I know that it has 1 proton. That's what the atomic number tells me. So in this case, I have 1, 2, 3 positive protons, which means the element that is made up of these atoms would have an atomic number of 3. So if I had to find that in the periodic table, I would go to number 3 and find that it's lithium. And this has to be an atom of lithium because it has 3 protons and the atomic number is 3. They have to match. So the atomic number tells me how many protons are in the atoms of a given element. So what have we learned here? We need to know that atoms are what make up elements, which are pure substances. They only contain one type of atom. And even though we think of them as the tiniest building blocks for all the elements in the universe, there are littler parts, there are smaller parts within the atom called subatomic particles. There's 3 of them. Positive protons, neutral neutrons, they both live in the middle in the nucleus, And then the negative electrons, the third and final subatomic particle, orbits round about the outside of the nucleus. And we can tell what element an atom belongs to by looking at the atomic number, which is just the number of positive protons in the nucleus. So we now know quite a lot about atomic structure. So we know what's inside an atom. We know about the atomic number, which tells us how many protons are in an atom. We know about the chemical symbol, which tells us what element the atom belongs to. And we know about the mass number as well, which tells us the total mass of an atom. And we know how to write all that information, to represent all that information in something called nuclide notation. So now we want to know, well, what happens when atoms change? Because the number of protons, neutrons and electrons, some will stay the same, some will change, and when they change, they are given different names, and we need to know a couple of cases where this happens. So the first case of things changing in atoms we're going to look at is something called an isotope. So we're going to look at isotopes. So what is an isotope then? An isotope, or well, a pair of isotopes, are atoms that have the same atomic number, but they have a different mass number. So I'm going to underline these in the colours that I've been using to represent each subatomic particle. And that will hopefully become clear why I'm doing that as we go through this. So, isotopes are atoms that have the same atomic number but a different mass number. Atomic number underlined in red, mass number underlined in green. So far I've been using red to represent protons and green to represent neutrons. So we'll bear that in mind as we go through this. So, for example, hydrogen has 3 isotopes. There are 3 types of hydrogen that can exist that have the same atomic number but a different mass number. We have protium, deuterium and tritium. Those are the names. But more useful to us to actually understand why they're different and what is different about each one would be to look at the nuclide notation. Because again, that tells us all of the important information as a chemist that I'm looking for. I want to know the symbol, I want to know the atomic number, I want to know the mass number. So there they are. All of them are capital H's because they're all hydrogen. All of them have an atomic number of 1 because they're all hydrogen. The atomic number tells me how many protons an element has, and that defines what element it is. The thing that's different, as I said up here, is the mass number. That's what makes these isotopes. Same atomic number, different mass number. Now, we want to know why that is. So what is it that's actually changed then? The atomic number, as we've said, is exactly the same. In each case, it's just 1. So what does that tell me? That tells me for each of my isotopes, I have 1 proton. That's not changed. It's the same for each one. 1 proton, 1 proton, 1 proton. The mass number, however, has changed. For protium has a mass of 1, deuterium has a mass of 2, and tritium, like tri, has a mass of 3. So again, why is that? Well, as we've just said, because the atomic number is 1 in each case, each isotope must have 1 proton. That's a given. That has to be the case because the atomic number tells us so. What about the electrons then? Well, this hasn't changed either because they're still atoms. And if they're still atoms, they have to be neutral. And if they're neutral, they have to have no charge. And if they have no charge, they have to have the same number of positive protons and negative electrons. So they must have 1 electron each as well. So that's not changed. So the only thing left that could have changed is the number of neutrons. So thinking back to the previous video where I spoke about nuclide notation and how to work out the number of neutrons we have, remember it was the mass number take away the atomic number. Because the mass number tells me all the protons plus all the neutrons, whereas the atomic number just tells me protons. I'm interested in neutrons. So if I can take the number of protons away from the total, I'll be left with just the neutrons. So we'll do that for each one. So mass number, take away atomic number. 1 minus 1 is going to give me 0. So protium has no neutrons, according to our calculation. What about deuterium then? So mass number, take away atomic number. 2 minus 1 is 1. So deuterium has 1 neutron. Okay, so that has changed. Tritium then, mass number, take away atomic number. 3 minus 1 is 2. So the thing that makes these isotopes, the thing that has changed, is the number of neutrons. So if we were to reword our definition then, we could say, as well as isotopes being atoms that have the same atomic number but a different mass number, we could also say that isotopes are atoms that have the same number of protons but a different number of neutrons. And that's what changes the mass number. So when you're thinking about isotopes, just 3 important things to remember. They're still the same element, right? That hasn't changed. Yes, they're all isotopes of each other. They are different, but they're all types of hydrogen. It's just like a variation, okay? It's like a different costume, if you like. Point 2, they have a different number of neutrons. That's what makes them isotopes. That's what makes them have a different mass number, because the atomic number hasn't changed. The number of protons and electrons hasn't changed. It must be the neutrons. And then thirdly, the properties aren't affected either. So hydrogen is still hydrogen. It's still a reactive, highly flammable, volatile gas in each case. It's just that deuterium is slightly heavier than protium and tritium is slightly heavier than deuterium. They are all still hydrogen. So isotopes then are atoms that have the same atomic number but a different mass number. And that's because they have the same number of protons but a different number of neutrons. In a previous video talking about subatomic particles and atomic structure, I mentioned how atoms can have different numbers of neutrons. And that was really important because that resulted in isotopes. And these were atoms of the same element that had different mass numbers because they had a different number of neutrons. Because the neutrons and the protons were the 2 subatomic particles that told us what mass an atom has. Now, neutrons are not the only subatomic particle that can change. What's important to remember is that it's not the protons. The protons always stays the same because that tells us what element it is. And it's not the neutrons because, well, we've already spoke about those. That would give us isotopes with different masses. But the third and final subatomic particle that we're going to talk about changing is the electrons. So we're going to talk about something called ions. So atoms, as well as being able to have different numbers of neutrons, can actually lose or gain electrons as well. And they do this to become more energetically stable, which I'll talk about in a little second. But the important part is that the newly formed particles, as a result of this change, as a result of losing electrons or gaining more electrons, are called ions. So if I lose even 1 electron or gain even 1 electron or more, I am no longer an atom because I don't have the same number of protons and electrons anymore. Okay? If that happens, if the electron number changes, then the charge is going to change from 0 to either be positive or negative, because that balance of positive protons and negative electrons has changed. They're not an even number anymore, they're not an equal number anymore. And that mismatch, that different number of electrons to protons, means that the atom has become an ion. So why does it do that? Why does that happen? Well, the 2 main reasons are atoms really want to be like the noble gases. So thinking back to the periodic table, we have a few main groups that were very important to remember. I spoke about the alkali metals, I spoke about the halogens in group 7, and I spoke about the noble gases right at the end. And we either called that group 8 or group 0. Now why is this important? Because elements that are in this end group, this group 8, all have a full outer shell of electrons. So in the previous video, we spoke about electrons and electron arrangements. If you haven't seen that, go watch that first. But the main point is, everything in this group, all of its atoms, all of these elements' atoms, their outer electrons, the shell that they occupy, or the orbital that those electrons occupy, are all fully filled. They're all full. So all the other elements in the periodic table want to be like that because it's stable. It's a really stable energetic arrangement because they have full outer orbitals. So noble gases are the ones to be like because they are stable. So we're going to learn a bit more about this by looking at two main examples. We're going to look at what happens when electrons are lost and why that might happen. And then we're going to look at what happens when electrons can be gained by an atom as well. So we're going to start off with an example of a metal, calcium. And calcium reacts, like all or most metals do, by losing outer electrons. So what does this look like? Well, I've drawn out, first of all, an atom with the nucleus with protons and neutrons inside, and then the electrons are orbiting the nucleus as I demonstrated in the previous video. So they fill these energy levels called orbitals in a very exact way. It's not random, they're all organised. So in this case there are 20 electrons, so that means we need 1, 2, 3, 4 total orbitals to fill in all of those electrons. So what happens? Well, in certain reactions, calcium will lose this electron here and this electron here. Now, why those two? Why not the two in the middle? Or some from the inner orbitals? Well, these electrons on the outside are the first electrons that other substances are going to come into contact with. They're the easiest to pull off because they're on the outside. These are the ones that things come into contact with first. So they're the first ones that are going to be lost. It's always the outer electrons that we want to consider when we're thinking about reactivity or chemical reactions, or really any kind of chemical change in elements or atoms. It's the outer electrons that do all the work, if you like. So what happens is, these two electrons are removed or pulled off or donated to something else in some kind of reaction, and we are left with 2 less electrons, which means we don't even need to draw in that fourth shell anymore. It's not needed because those electrons are no longer orbiting this atom, this atom's nucleus. So they're away doing something else. They've reacted and we're left with this. Now the question is, what charge does this substance, this particle, now have? Well, if it's lost some negativity, it now has more protons than it does electrons, meaning I have formed a positive ion. I've went from being neutral, 20 protons, 20 electrons, to having a positive charge, because I've still got 20 protons, but now I've only got 18 electrons. These other 2 have left to go and react with something else. So if I lose electrons, I form a positive ion, and that is very important to remember. So losing negative electrons forms a positive ion. And very importantly too, we can no longer call this thing on the right hand side an atom. It's not an atom anymore because it's not electrically neutral. It does not have the same number of protons and electrons, so it's now an ion. And it's a positive ion because it's lost electrons. And the way that we show that is by a little plus in the top right hand corner and a number in front of that plus, in front of that symbol, to show how many positive charges. Since it's lost 2 negatives, we're going to have to fill it in with 2 positives to show that it has a 2+ charge overall. So that is the first example. The second example is what happens when the opposite happens. Because it's not just that electrons can be lost, they can also be gained, again, through some kind of reaction. It's mainly non-metal atoms that do that. So we're thinking about the right-hand side of the periodic table now. So non-metal atoms react by gaining outer electrons. So for example, we could talk about chlorine. So I've done the same thing again, drawn out a full diagram of chlorine with my 17 protons in the middle and my 17 electrons around the outside. And this time, let's think about what is happening, because again, we have outer electrons and we have some kind of reaction happening. Now you could say, well, why doesn't the chlorine just lose electrons? Why don't all atoms just lose electrons? Why don't they all just gain electrons? Why don't they all do the same thing? Well, let's have a look at the outer electrons in chlorine's case and compare it with what we saw before in our calcium example. So this time we have not just one or two outer electrons, but 1, 2, 3, 4, 5, 6, 7 outer electrons. Now, removing an electron or gaining an electron isn't free, right? There's some energetic cost that happens. So ripping off an electron from an atom, which some other chemical will come along and do, is not cheap. It costs energy. So which do you think would be easier to do? To remove 2 electrons from an outer shell, like we did with calcium, or to remove 7 outer electrons? Well, of course it's going to be the calcium example. It would be much more difficult to remove all of these 7 outer electrons. But chlorine is still in a predicament, it's still in a problem, it still wants to be stable. It still wants to have a full outer shell of electrons. So how's it going to do that? Well, it's not going to remove all of these outer electrons. It's going to gain an electron from somewhere else. It's going to react with another chemical that can donate its electron to chlorine, and chlorine will tear it off of something else. It will steal it. So instead of losing its outer electrons, it gains one, and now look what's happened. Now chlorine has 1, 2, 3, 4, 5, 6, 7, 8. Perfect. It now has a full shell, a full outer shell of electrons. So in both cases, the calcium ion is now more stable, because in losing that outer shell, it now has a full outer shell. If you go down to the next layer of orbitals, it's got 1, 2, 3, 4, 5, 6, 7, 8. Good. It's stable. And the chlorine, by doing the opposite, by gaining an electron, now has 1, 2, 3, 4, 5, 6, 7, 8. A full outer shell, a full outer orbital of electrons. So the calcium ion and the chlorine ion are now more stable as a result of either losing or gaining electrons. And we do a very similar thing to show that reaction when we gain electrons. We draw our atom, which is just a chemical symbol with no little symbols at the top. What's happening with the electrons? In this case, we are gaining an electron, so we're adding it on. And the result is the opposite of what happened before. We now have a negatively charged ion because this particle has more electrons than it does protons. It has 17 protons, but now it has 18 electrons. So it's got one negative charge. And notice before we drew a little number 2. If there's anything in chemistry that we need to draw a 1 for, we just leave it out, because it's implied that there is 1 there because we've drawn a little symbol. So 1 chlorine, 1 electron, 1 chlorine. We don't draw number 1s next to these. If there's a number 1, we just leave that part out. So it's just 1 negative by drawing just the negative sign on its own. So negative ions formed because we've got 1 more electron than we do protons. And that's, again, important to remember. So if we gain negative electrons, we form a negative ion, because now we've got more negativity than we do positivity. So just to summarise, ions are charged particles formed when atoms lose or gain electrons. And they do this so that the atoms can become more stable. So they want full outer shells or full outer orbitals of electrons. And in doing so, they either lose or gain electrons. If they gain electrons, they have become more negative. So they form negative ions. And if they lose electrons, if they lose negative particles, they become positive ions, positively charged ions. So previously we touched on the idea that compounds from different homologous series can have the same molecular formula, they can have the same number of atoms, but they have a different structural formula. They can be arranged in a different way. And we called pairs or sets of these molecules and compounds isomers, because that was how they were. They had the same molecular formula, but a different structural formula. And in looking at that, it raised a couple of key questions. And we want to look at one of those questions in detail in this video. So we're going to talk about isomers, but we're mainly going to look at how we name different hydrocarbons that are a little bit more complex than the ones we've seen already, because they have kind of extra bits added on. So the question we really want to focus on here is, can isomers exist within one homologous series? So do I need to go between different homologous series, or can I choose one, for example the alkanes, and find isomers within that homologous series on its own? Well, let's start with a simple molecular formula. Let's just go with an alkane, and let's look at C4H10. So without this being named, what can we infer from this molecular formula? Well, we know it has 4 carbons and 10 hydrogens. That's what the molecular formula tells me. But other than that, it doesn't really tell me too much. I have to decide how these atoms are going to be arranged, how they're going to be structured, if I'm not given any additional information. So let's have a go at how we might do that. So we could, of course, draw it out the way that we learned in the alkanes video. Nice and simply, we have a straight chain of carbon atoms all joined together, and then we just make sure that every carbon in the chain has 4 bonds coming off of it to get to a valency of 4. So let's go through and make sure that this is definitely correct. So is it an alkane? Well, yes it is, because it follows the general formula of the alkanes. CN, H2N plus another 2. So yes, it is an alkane. Does it have the correct number of atoms? 1, 2, 3, 4 carbons. Yep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Yes, it does. Is it saturated? That is another prerequisite of being correct for an alkane that we need to include. Well, yes, because it's all single bonds. All of the carbons are joined together by single saturated bonds. So yes, it is. So that's completely correct. That is a completely acceptable full structural formula for C4H10. And in fact, we know this to be butane. And it's ane because it is an alkane, which all the alkanes end in ane, and we use the but prefix to show that we have 4 carbons. Great. Is that the only way that we can draw C4H10, however? Well, maybe not. Let's have a think here. If I were to take one of my carbons in this chain and pull it off, so let's say this one here, let's say I just break this bond here, pull that off, and I pop on one of the hydrogens that's left over on this pulled off bit back onto the chain to form a smaller chain. Okay, then I'd have one less carbon. But then I could just pop that carbon that I've pulled off into the middle and form a different shape. So now I've got the correct number of carbons, and they are all singly bonded to one another, but they're arranged in a different way. They're not in a straight line. They've got multiple paths. If I go from this side, I travel along, and I get to this central carbon here, I could go up, or I could continue along. I have different paths. It's almost like a branch has formed. And now all I need to do is make sure every carbon has 4 bonds around it so that it is correct. So 1, 2, 3, 4. 1, 2, 3. This one needs an extra one. 1, 2. Okay, I need another 2 here. And then at the top, I only have 1 bond on this carbon, so I need an additional 3. So let's see what happens when I populate those empty bonds with hydrogen atoms. Okay, looks a bit funky, but let's check and see if it passes all the tests that we gave this first compound. So again, is it an alkane? Well, does it follow the general formula? Yes, it does. Does it have the correct number of atoms? 4 carbons, 1, 2, 3, 4. Yep. 10 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, it does. Is it completely saturated? Does it only contain single bonds between the carbons? Yes, it is. So, if this butane molecule passes all these tests and fits into that formula, but so does this one, is this also butane? Or are we going to have to come up with a naming system that is a little bit more detailed to be able to tell the difference between a C4H10 that looks like this and a C4H10 that looks like this? Because what we have just discovered is that the answer to the question is in fact yes, you can have isomers that exist within one homologous series. Because here we have a simple alkane, and the only difference between these two full structural formulae is the structural formulae. They have the same molecular formula. They are both C4H10, so they have the same molecular formula, but they have a different structure. And that is our definition of an isomer. So now that we've answered that question, we want to be able to say, well, can we come up with a better naming system rather than just make sure it ends in "ane" and add on a prefix? Because we've just discovered that that is not quite detailed enough to give us all the information that we need about this structure. So that's what we're going to look at next. In the previous video, we found out that we can in fact have isomers, which were, remember, the same molecular formula but a different structural formula between compounds. We can have isomers existing within one homologous series. And in that video we looked at C4H10, which was an alkane, but we found that we could draw it in a couple of different ways. We could give it a couple of different structures. So now what we want to do is come up with a better way to name these structures so that we can tell the difference between them, because now butane is not detailed enough, because this is butane, but this is also butane because it follows all of these rules. So if you've not watched that previous video, watch that one before continuing on with this video. So to answer that question, to be able to name these molecules, these structures a bit more detailed, in a more detailed way, we're going to look at something called systematic naming. And this is extremely important in chemistry, all right through up past National 5. And what this enables us to do is to use the structure itself to give the compounds a more accurate name, rather than just simply butane. And that will enable us to tell the difference between different molecules, different isomers, different structures based on their structure. So what I'm going to do, I'm going to show you this structure here, and we're going to take our time and go through the systematic naming process in detail to come up with a detailed name for this compound here. So if we look at it, we can see that it's slightly different from the compounds that we've looked at so far. Now it is in fact an alkane, which we'll prove in a little second, but looking at it, what can we see already? Well, we can see that it's a saturated compound, it's a saturated hydrocarbon. How do I know that? Well, it's saturated because it only contains single bonds, and it's a hydrocarbon because it only contains hydrogen and carbon. So we know that right off the bat. Now, what we can also see is that it's not a perfectly uniform straight chain. There's a little kind of extra carbon thing going on up to the top left here. And that is what's going to present us with some issues, because we can't just give this a simple name like we did before, like butane or pentane or hexane, just based on the number of carbons alone. We have to detail where those carbons are and what other carbons they are bonded to. That is what's really important here. And there's a few rules that we use to do that. So, first of all, we have to identify the longest chain of carbon atoms that are all bonded in one line, one continuous chain. And to do that, I'm going to start using a couple of different colours so that this is really clear. All we're going to do is look for that. We're going to look for the longest chain of carbon atoms. So I'm going to start from the left. I'm going to suggest that we go right through to the right. So we have 1, 2, 3, 4, 5 carbons. So 5 could be our longest chain here. Now, we could also start from this carbon here because this one is joined onto this one. And then we have two choices. We could either go left or right. So if we go 1, 2, 3, well, that's not very long at all. That's certainly not as long as 5, so that's not the longest chain. But we could go 1, 2, 3, 4, 5, because those carbons are all joined in a line too. So we're left with the choice between 5 this way or 5 this way. And the answer is, both answers are actually acceptable. But for just now, we're just going to stick with what looks the easiest. Okay, which is the easiest to look at, and that is to just identify the straight chain in the middle or at the bottom as the longest chain. So I'm going to draw a blue box around that just now, just to show that that is our longest chain, and we have 5 carbons in it. So that's the first step. Second step would be to number these carbons, and we want to start at the most exciting end. So by exciting end, all I mean is the side that actually has something interesting going on, whether it be one of these branch things or some kind of functional group, which we'll look at in later videos. But the side that has the most going on. So clearly in this case, if we choose between the left side and the right side, it's the left side that's the most exciting because we've got this kind of branch thing going on here. So we're going to number them starting at the left. Now please note, it will not always go left to right. In this case it does, because the left happens to be the most exciting end. But always look out for that. It might be the right, it might be the bottom, it might be the top, who knows. Just always look for the most exciting end, the side with the branches or the functional groups. So going with that, we're going to say that this is carbon 1, this is carbon 2, and so on. 3, 4, and 5. Okay, so that's that done. So now we know we have 5 carbons in the longest chain. This is already going to help us because we know how to name an alkane with 5 carbons in it. We already know how to do that. So that's going to come in handy in a second. The final step then is to name and number any branches that we find on the structure. So let's have a look. We have our nice straight chain of carbons going across the middle, but then we've got this guy up here. We've got a carbon atom with 3 hydrogens joined onto it. There is a name for what that is. That is a branch, and it's a branch because it branches off of the main chain. Now branches themselves have to be smaller than the main chain because of course we've looked for the longest chain at the start, so anything coming off of it should be shorter than the main chain itself. And at National 5 level there are 2 branches that you have to remember, you have to be able to identify and name. So first off is the one that we have right here. Single carbon with 3 hydrogens coming off of it. And the second is a chain with 2 carbons with 5 hydrogens coming off of those. And I'll just draw a little squiggly line just now to represent that these are joined onto the rest of the main chain. And these have names of their own. If we see a branch that looks like this, it has a C with 3 hydrogens on it, we call that a methyl group. And if we have a branch with 2 carbons and 5 hydrogens coming off of it, we call that an ethyl group. And these shouldn't be too difficult to remember because they match the prefixes that we already know for naming alkanes and alkenes and cycloalkanes. We've got the meth or meth part for 1 carbon, same as methane, and we have the eth or eth part for 2 carbons, like ethane or ethene. So what we want to do is use that knowledge of what these branches are called to name and number the branch that we have in our compound. So by name, I just mean choose one of these names to match however many carbons are on the branch. And by number, I just mean indicate which carbon of the main chain it is bonded onto. So if we have a look at our structure, this branch, which happens to be a methyl branch, is bonded to carbon 2 of the main chain. So it's 2-methyl is the name of our branch. So now we have all the information that we need to actually name this systematically. So the way that we do it is we just go through the rules. And one by one, we make sure we include all of the information to show what our structure is all about. So in our main chain, we have 1, 2, 3, 4, 5 carbons. Because we have 5 carbons, we know that this structure is some kind of pentane. Because it has 5 carbons in the main chain, we use a pent. And it ends in ane because it is an alkane, because it's all saturated single bonds. And it follows the alkane general formula of CnH2n plus 2. Now I know what some of you are thinking, well, how can it be pentane? We've got an extra carbon here. Does that not make it hexane because there's 6 carbons altogether? Well, yes and no, because that extra carbon acts as a branch. So we name it and number it like a branch. It's on carbon 2, so we're going to call this 2 something, and then we're going to use a dash, and we're going to name what type of branch it is. In this case, it is a methyl branch. So our full systematic name for this compound is going to be 2-methyl pentane, because we have 5 carbons in the longest chain, and we have a methyl group on carbon 2. And you'll notice that when I'm separating numbers and words in systematic naming, I use a dash, and that just keeps things nice and neat. So that gives us a starting example of how to systematically name a hydrocarbon compound. What we're going to do in the next video is look at a few more examples that are a little bit more complex, so that we can see this process in a bit more detail. Following on from my previous video on systematic naming, we're now going to have a look at some more examples of alkane compounds that require systematic names to be given an accurate name to show what is in their structures. So what we're going to do is have a look at our second example, which follows on from the previous video's first example. And this time, this is what our compound looks like. So we're going to have to remember our rules for systematic naming here to approach a systematic name for this compound. So if we think back, rule number 1 involved picking out what the longest chain of carbon atoms was. We've got a few choices here, so let's go through them in detail. So just like the last video, we could go through it and say, well, let's just take the one that goes right through the middle. That's always a good option to start with. So we have 1, 2, 3, 4, 5, 6 carbons going along the centre here. So the longest chain could be 6. Let's try a different way. 1, 2, 3, 4, 5. Okay, so it's not that one because that only has 5. 1, 2, 3, 4, 5, 6. Well, we could go this way and up as well. So we have a choice. We could either go right along the middle or right along nearly to the end and then up. Just like the previous video, I'm going to stick with what is the easiest to look at. So I'm going to take the blue box and put it round the longest chain in the middle. Step 2, we now need to identify each carbon in that chain by a number, and we start at the most exciting end. So I'm going to let you have a look at that, have a think. Which end do you think is the most exciting? Which end contains the most branches or functional groups? And of course it is the right hand side, because there's really nothing at all going on at this left hand side. It's just a straight chain, whereas on the right side we've got a couple of branches going on. So we're actually going to number from the right hand side this time. So we're going to go 1, 2, 3, 4, 5, 6. So already we know we have some kind of hexane here because there are 6 carbons in the longest chain. It's now just a matter of identifying, naming and numbering any branches that we have. So we have a branch here and we have a branch here. So we have a branch on carbon 2 and a branch on carbon 3. So now given that we know the names of these branches are methyl branches because they contain one carbon, we have enough information to actually go ahead and systematically name this compound. So as I say, 6 carbons in the longest chain, so we know that this is some kind of hexane because it's an alkane, and we have 2 branches. Now this is slightly different from our previous example because if we have more than one of the same type of branch, we need to use a little extra prefix, which I will show you now. So we have a methyl group on carbon 2 and a methyl group on carbon 3. So we're going to indicate that by saying we have 2, 3 dash dimethyl hexane. So what have I done here? If we have multiple branches, we list the numbers that those types of branches are found on. So my methyl groups, my methyl branches are found on carbons 2 and 3. I have 2 of them, 2 methyl branches, 1 on 2, 1 on 3. Because there's 2, I can't just say methyl, I have to indicate that there's 2 by saying dimethyl. If there were 3, I would list 3 numbers of carbons that those branches were contained on, and I would say trimethyl. The idea of this prefix is just to indicate how many of the same type of branch are found on the hydrocarbon. So overall, the systematic name for this hydrocarbon is 2,3-dimethyl hexane. Let's look at another one. So this time we have a slightly different looking molecule. It looks as if it goes up and down rather than left and right. And that is important to consider because remember, atoms, molecules, compounds, they're mixtures of millions and millions and billions often of atoms. And they're all arranged relatively randomly and they all move around. So we're never going to find perfectly ordered molecules like this in nature. So we have to consider them at different angles and different shapes as well. Always imagine these things as they exist in 3D. But anyway, let's get back to the naming. So we have our longest branch, our longest chain, sorry. Let's see if we can identify that. So we could use our tried and trusted method of going across the way, and we could have 1, 2, 3. That's not really looking like the best option though. Or we could go from top to bottom, 1, 2, 3, 4. Okay, but that's not quite the longest chain because once we get from the bottom to the top, we can then add on an extra carbon. Right, these are all in one line, and these are all in one line. So it's just a matter of choosing which direction I want to go. It doesn't matter because either way I go, I'm going to have 1, 2, 3, 4, 5 carbons, or 1, 2, 3, 4, 5 carbons. So it's up to you. In this case, let's go to the right. So I'm going to draw a box around my longest chain. And then, same as before, all I need to do now is number the carbons in that chain starting at the most exciting end, and that's the side with any branches or any functional groups. So in this case, it's the side nearest this carbon, because straight away I've got this branch, whereas if I started at this side it would take me ages to get to this branch. It would take me more carbons to get there. So I'm going to start at this side. So I'm going to have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And now the last step, identify and number any branches. Here's a branch right here, and it's on carbon 2. So we know the process by now. We have a methyl branch on carbon 2, so we're going to call this 2-methyl, and it's 1, 2, 3, 4, 5 carbons in the longest chain, and it's an alkane, so it's 2-methyl pentane. And the reason why I've chosen this example is because if we think back to the previous video, this is actually the exact same compound that we named before. This here is also 2-methyl pentane. I've just drawn it slightly differently. So you can imagine that in this example, if I had went from carbon 5 here up to carbon 2 and then out here and selected that as my longest chain, it would have looked somewhat like what we have here. It's just that this carbon up here has been twisted off to the side. So always bear that in mind. Even though they look slightly different, if you go through this process for systematic naming and you're really careful with numbering the longest chain and selecting any branches, you will find that compounds that initially look like they might have a different structure, they might look like they are isomers, but they are in fact the same thing, or maybe even a mirror image of the same thing. Now I'm going to do a video on that later on so that we can better identify pairs of molecules that are isomers and ones that are not. But for just now, just bear in mind that you have to be very systematic and very careful with how you go through these rules, and just make sure you always select the longest chain properly and you always name and number any branches properly as well. So what we're going to do now is we're going to move on to not naming molecules from their drawings, their structural formula, but we're going to do the opposite. We're going to look at some systematic names and see if we can come up with the drawings ourselves. So in example number 4 then, we have 3-methylpentane. So simple enough, all we have to do is remember our 3 rules. The exact same 3 rules apply for doing this in the reverse as well, if we start with the systematic name and we want the full structural formula. So all we're going to do is start from the longest chain. How are we going to know what that is? Because it's contained in the last part of the name here, pentane. So because it's some kind of pentane, I know that I have to draw 1, 2, 3, 4, 5 carbons. Now that I've got my straight chain down, I'm going to stop there and I'm going to go back to the name and consider where my branch has to go and what type of branch it is. And the reason I'm doing that before I draw in any extra bonds to these carbons is so that I can draw it nice and neatly and so that I can fit things in around one another. So it says 3-methyl. So that means on carbon 3, I have to include a methyl group. Now in this case, I have 1, 2, 3, 1, 2, 3. Doesn't matter which side I approach it from, the methyl group's actually going to be bang in the middle. So I don't need so much to pay attention to numbering these carbons in this case, because the result will be the same either way. They would be mirror images of each other. So we're going to put our methyl group, let's do it going down the way this time, just for a change, because that is allowed. There's my extra carbon, there's my methyl carbon, and now what we need to do, just like we always do, is make sure every carbon has 4 things bonded to it, 4 bonds coming off of it. So in this case at the start we have 1, so we need an extra 3. This carbon already has 2, so let's include another 2. This carbon in the middle has 3, it's nearly there, so it just needs an extra 1. And we go through each carbon and do the same thing, so that we have the correct number of bonds coming off of each carbon to add to 4. And all that's left to do, because this is a hydrocarbon, is add in all of the hydrogen atoms to make this an accurate full structural formula, and make sure you don't miss any on your branches either. And there we have it, that's 3-methylpentane. Okay, slightly trickier one then, but if we remember our rules, it should be nice and easy. This time we've got 2, 2, 4 trimethylhexane. It seems complicated at first, but it should be nice and easy if we just go through gently using our rules. So we'll do the exact same thing. We have some kind of hexane. What does that mean? That means I need 6 carbons. 1, 2, 3, 4, 5, 6. It's ane, so it's an alkane, so they're all saturated, they're all singly bonded, so that is fine. And now we need to decide, well, which side are we going to start from, because we have 2, 2, 4 branches to deal with. And they're all methyl branches. And this time you'll notice something we've not seen yet. We have 2 of the same number. Now what does that mean? That means we have 1, 2 methyl branches, both on carbon 2, because I've used the number 2 twice to indicate that there's 2 branches on carbon 2. Okay? So let's just go from the left hand side for simplicity's sake. Let's number our carbons to keep it right. 1, 2, 3, 4, 5, 6. Once you get good at this, you don't have to actually write down the numbers, but just for just now, so it's nice and clear, I will show you those. And we need to lay out where our branches are going to be. So we have carbon 2. We have to have 1, 2 methyl groups on carbon 2. So we're going to draw in one at the top and one at the bottom. Okay, so that's that one done and that one done. Nearly there. Next step, on carbon 4, we need another methyl group. So let's just add that onto the top. I could add it onto the bottom, it doesn't really matter, as long as it's on carbon 4 directly. And now I've done my 4th methyl. So now let's count, 1, 2, 3, I have my tri-methyls. I've got 3 methyl groups ready to go. That wasn't too bad. I just need to pay attention to how many branches I have, what kind of branches they are, and where they are found on the molecule. Last step is the easy fun one. I now just need to go through every carbon that I have and make sure they all have 4 bonds. I did that nice and quick, but make sure you are counting when you're doing that process. And then of course all that remains is to make sure we add on all the hydrogens on all the bonds. And the way that I'll do this, you notice, is I will go through each carbon systematically. I'll go in order of the carbons to make sure that I don't miss anything. But you can come up with any order that you like as long as you stick to it. Now what I want to do here to finish is just to prove to you that this is an accurate way of naming these homologous series. This looks quite complicated. Are we convinced that this is definitely an alkane? How would we check that it's definitely an alkane? Well, we could use the general formula. If this is indeed an alkane, it should follow CnH2n plus 2, shouldn't it? Because that is the general formula. So let's go ahead and check. So, how many carbons do I have in total? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I have 9 carbons. If this is indeed an alkane, I should have 9 times 2 plus another 2 hydrogens on this structure. And that way we'll know that we've done it correctly. So let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 is 9 times 2, which gives me 18, plus another 2, and that's 20. So we know that this is definitely an alkane because it follows our general formula for the alkanes. And that is how we systematically name alkanes. In future videos, I will explore how to systematically name our other homologous series that we've looked at, so the alkenes and the cycloalkanes as well. But for just now, these are the basic rules that you need to follow to systematically name alkanes. In the previous video, we looked closely at how to test the difference between a cycloalkane and an alkene using bromine solution, because the alkene will quickly decolorize bromine solution, whereas the cycloalkane will not. And we decided that the reason for that is the double bond in the alkene is used up in what is called an addition reaction with the bromine solution. So in mentioning that that was an addition reaction, what we now need to consider is that there's actually 3 different types of addition reaction at national 5 level. And they all involve a compound that adds across a carbon-to-carbon double bond. And because they require that carbon-to-carbon double bond, they all involve alkenes. So when we think of addition reactions, we're thinking of adding something across a double bond. So if we look at the first type, it should be very familiar to us because it's the one that we've already looked at. It's the bromine type addition reaction, and it involves any of the halogens. So bromine could be an option, or we could also look at fluorine or chlorine or iodine or the other halogens. So what we have is an alkene because we have to have the double bond present, and we add any of our halogens, so any of our diatomic halogen molecules, and what we form always is some kind of dihaloalkane. All that means is 2 halogen atoms adding across an alkene to form a saturated compound, dihaloalkane. And you'll notice it changes from ene to aim as well. So to illustrate that by example, we could have our double bond in this compound here, which contains 2 carbons, which makes it ethene, and we can add bromine across this double bond. So what actually happens then? Well, the way to draw it out as a full structural formula is to basically draw what we start with in terms of atoms. So I'm going to keep everything that I already had. I've got 2 carbons and 4 hydrogens. And all that happens is when it comes into proximity of this bromine molecule, the double bond will open up like a sort of gate. Okay, it goes from being a closed double bond to opening up. And that means our carbon atoms can now bond to something extra each. Because remember, carbon has to be surrounded by 4 bonds. So in this case, 1, 2, 3, 4. 1, 2, 3, 4. Now that that central double bond is just a single bond, we can add each of our bromines onto each of our carbons. And now if we try to name this, all we have to do is indicate which carbons the bromines are on, and then determine how many carbons we have. So we're going to in fact have 1, 2, dibromo, because there's 2 bromine atoms, eth, because there's 2 carbons, and it's an alkane, or a haloalkane now, because there are no more double bonds. So whatever the halogen is, we always form a dihaloalkane when we react one with an alkene, and that is halogenation, or halogenation, because we're adding a halogen. The second type we're going to focus on is very similar. In fact, it's the exact same mechanism, which just means how the reaction proceeds. But instead of adding a halogen, we're now going to look at what happens if we add a hydrogen, which is slightly different. So I could have an alkene, again, because I require that double bond in an addition reaction, and I can add a hydrogen. So I will use the same starting material. I will just stick with ethene to keep it simple. And remember, hydrogen is also a diatomic molecule, so there's going to be 2 hydrogens. Now, what happens when we add hydrogen across the double bond? Well, again, we keep all the atoms that we had before, 2 carbons or 4 hydrogens. We open up the double bond and we add in the chemical that is being added. And you'll notice that instead of now having an alkene, very simply, I've actually formed an alkane. Because that is the difference between an alkene and an alkane. We simply have CnH2n, CnH2n plus 2. Here's my plus 2 hydrogens. And adding 2 hydrogens to an alkene, I can form an alkane. And that can be quite a useful reaction if you start with an alkene but you actually in fact wanted an alkane. So, in forming this new alkane, I can call it simply ethane, because all I've done is add 2 hydrogens to ethene, which breaks the unsaturation, forming a saturated alkane compound. So in a hydrogenation reaction, we form an alkane from an alkene. Which brings us to the third type and the last type, which is very similar sounding, but is quite different. And that's a hydration reaction. So that's not to be confused with hydrogenation, because hydration, in fact, involves water instead of hydrogen. And that makes things a little bit different. Now, why is that? Well, because water is not a simple diatomic molecule. There's not 2 atoms, one which neatly goes onto each carbon. This time, we have to consider that water looks like that. We have 1 oxygen and we have 2 hydrogens. We actually have 3 atoms that all have to go somewhere here. So, what we want to do is the same thing again. We always start at the same. We know that the double bond is going to be added across. So, we turn it into a single bond. Add in what we already had. And I should note as well, I could flip this round, I could draw the hydrogens that I had at the bottom as well, it doesn't matter, as long as each thing that I'm adding goes onto each carbon of the double bond. That is very important. But for just now, let's just stick with drawing them at the top to keep it simple. going to retain all those hydrogens, and this time what's in fact going to happen is I'm going to break one of these bonds in my water molecule. At this stage it doesn't really matter which one, as long as you know that one carbon is going to have a hydrogen added to it from this part of the water molecule, and the other carbon is actually going to get both an oxygen and a hydrogen added from the other part of the water molecule. This group here is actually a very important group. This collection of two atoms, this functional group. It's actually called a hydroxyl group, and we'll look at that more in the next topic in Unit 2. But for just now, what we need to know is that when we add water to an alkene, what we've actually formed is an alcohol molecule. And we can tell it's an alcohol because it has this O and H joined onto it. So we went from ethene to ethanol, which is one of the simplest alcohols that we can form. And as I say, this will be the focus of the next topic. But for just now, what we need to know is that these are the three different types of addition reactions involved at National 5. They all involve alkenes. They all involve adding a compound across the alkene's double bond, and they are halogenation, where we add a halogen, hydrogenation, where we add a hydrogen molecule, or hydration, where we add water. And we need to know what we form in each of these reactions. A dihaloalkane, an alkane, or an alcohol.